Power supply design and filtering often dictate the ultimate performance of an electronic circuit. In radio frequency and sensitive audio applications, the power supply is practically part of the signal path. If the DC power isn't perfectly clean, that noise will inevitably mix with your signals, causing hum, instability, or masked signals. Here is a breakdown of how power supplies generate DC and the filtering strategies used to keep that power clean across different stages of a build. The primary job of a standard AC to DC linear power supply is to step down the mains voltage, convert the alternating current into pulsating direct current using a rectifier, and then smooth those pulses into a flat line. The workhorse of this smoothing process is the reservoir capacitor or filter capacitor. It charges up when the rectified voltage peaks and discharges into the load when the voltage dips. The slight drop in voltage between pulses is known as ripple. For a full wave rectifier, the peak-to-peak ripple voltage can be approximated using VR approximately equal to I divided by 2FC, where VR is the ripple voltage peak to peak, I load current in amperes, F AC line frequency in hertz, example 50 hertz or 60 hertz, C smoothing capacitance in farads. When pulling high current such as the 15 to 20 amps required to drive a 100 watt linear amplifier, the load current I is massive. To keep the ripple voltage VR low enough to prevent distortion or hum on voice peaks, you need an exceptionally large capacitance C, often tens of thousands of microfarads. Here is an interactive demo of the filtering process in a full wave rectifier. You can see that there are pulses going on, which will be twice the frequency of the AC which is being rectified. Or we are starting with simple 10 microfarad capacitance and load resistance 10 ohms. Hardly any filtering is there. Now we are increasing the capacitance. See, filtering is occurring. And when the capacitance is 5000 microfarad, fairly good filtering. Additional filtering occurs with the load also, increase in the load. When the load is lower, load impedance is lower, the filtering is lesser. If you increase it, see, 200, 380, 400. So a large load resistance along with a large capacitance effectively smoothens out the output almost like a perfect DC. If you reduce the load resistance, there is a minor effect, but more effect is with capacitance. If you reduce the capacitance, the ripple amplitude is much higher. So I'll do it the other way around. I'll increase the load maximum. Even with 1000 ohms load resistance, there is plenty of ripple. If you have a good capacitance, here the capacitance is only 10 ohms, 10 microfarad. So effect is more for the capacitance, and there is some effect for the load also. So that's the principle of full wave rectifier with a good filter. This does not show the effect of a choke. There will be additional effect for a choke also. Moving on to RF and high frequency filtering. Bulk smoothing only handles low frequency mains hum. It does little to stop high frequency noise from switching regulators, digital logic boards, or stray RF from entering the power lines. When dealing with low-level RF signals like measuring millivolt VFO outputs or running a digital SDR setup, even millivolts of high-frequency noise can introduce severe instability. Bypass or decoupling capacitors. A large electrolytic capacitor is physically too slow, due to internal inductance to react to high frequency noise. Therefore, smaller ceramic capacitors, typically 0.1 or 0.01 microfarad, are placed as close to the power pins of active components as possible. They act as a dead short to RF, shunting high frequency noise directly to ground before it can enter the component. RF chokes and inductors. While capacitors shunt noise to ground, inductors or chokes block it from traveling down the wire. Placing a molded RF choke or winding the power cable through a ferrite toroid creates a high impedance barrier to RF, keeping transmitter energy out of the power supply and keeping digital hash away from the receiver. Moving on to a comparison between linear versus switching power supplies or SMPS. Choosing the right type of supply heavily impacts your filtering strategy. Linear power supplies, they use a heavy ion transformer, a rectifier bridge and large capacitors. Though they are physically heavy and inefficient, they are electrically quiet. They are the gold standard for analog radio transceivers because they generate almost zero high frequency noise. Switching supplies, SMPS. These are lightweight, highly efficient and can deliver high current, ideal for powering single board computers like a Raspberry Pi. However, they operate by switching power on and off at high frequencies, often 50 Hz to over 1 MHz. This generates significant switching noise. If an SMPS is used near sensitive radio equipment, it usually requires aggressive external LC, inductor capacitor, filtering and proper shielding to prevent it from acting like a broadband jammer.